the way I'm going to do today's lecture is we'll go over the materials or each topics we went over in previous chapters, starting from chapter 4, acid-base, and then we have the chapter 5, the physical properties, nomenclature of alkanes, the premier, which is like reaction mechanism, thermodynamics, arrow pushing, etc. And then talking about reactions of alkenes and alkynes. And hopefully we'll have time to do some example questions together. If not, you can always refer to the annotated note for the example questions, all right? So let's get started. So the acid-base chemistry has been a while, so I think this might be a good opportunity for us to review what's being discussed. Now, first of all, in acid-base chemistry, terminologies, right? If we ask you, what is a Bronsted acid? We're saying that is a proton donor, and a Bronsted base will be proton acceptor, right? So we're talking about transfer of proton in an acid-base or Bronsted acid-base reaction. Then for Lewis acid base, we have a different set of definition. Lewis acid, we're talking about electron pair acceptor, or we also call them electrophilic. Lewis base, we call them electron pair donor or nucleophilic. So in organic chemistry, we're almost always working on this concept of how does the electron move in an elementary step. All right, so we always want to pair it up. A nucleophilic site with an electrophilic site, a nucleophile with a electrophile, a Bronsted acid with a Bronsted base. Or sometimes you can also pair it up different, like an alkene reacting with H+. So in that case, you can also treat it as acid-base reaction, right? So your H+ is being transferred onto your alkene. So these are basic terminologies. And then this is the first time we introduced the concept of arrow pushing. Like, for example, how to use arrow pushing to demonstrate this Bronsted acid-base reaction. Why this Bronsted acid-base? Well, the left molecule is losing a hydrogen, and that hydrogen got transferred onto your right molecule, which is your ammonia, right? So if we're doing the arrow pushing, we're seeing the electron comes, reacting with the hydrogen or grabbing the hydrogen to form a new NH bond, and the electron got pushed in the OH bond, got to push onto the oxygen, right? So when we're doing the arrow pushing, we always start from the source of the electron and then move it to the end of the electron. And in this process, I expect you to know how to label each thing. What's the identity of each species? Like this one, the first one will be my Bronsted acid. The NH3 is my Bronsted base. And the third one will be my conjugate acid, a conjugate base of the original acid. And then the NH4 plus will be the conjugate acid of your NH3. All right. And what about Lewis acid-base reaction? Well, Lewis acid-base reaction, we're talking about electron pairs. So no proton transfer is taking place. In this case, the Lewis base will be moving onto the Lewis acid. Your aluminum chloride, the aluminum center, does not have 4 valence of electron or 4 octet of electron, and hence it's an electron deficient site. So when we push the electron, we do it this way. All right, and what we're forming here is a Z-ion or a charge-separated species. So these are quick reviews on rules of arrow pushing in acid-base chemistry. In chapter 4, we also discussed some more of a calculation kind of question, very light, but still it's one of the fundamental skill of chemists, knowing how to calculate pH, coming from pKa and concentration of an acid solution. Right, so knowing how to calculate pH, pKa, and also how to use pKa to justify the acidity of a molecule. Right. The take-home message, smaller pKa, stronger acid. And then in this part, we also have a brief discussion in thermodynamics or like reaction equilibrium. So when we talk about that, we have delta G naught, or the Gibbs free energy of the reaction, equals to negative RT ln K, where K is our equilibrium constant. So note the difference. Equilibrium constant is a product concentration over reactant concentration. Ka is specific for these aqueous acid-base reactions. So Ka is defined as equilibrium constant times the concentration of water, which is just a number. All right. And then some of the general chemical intuition of thermodynamics, or some of the terminologies. Negative delta G naught. I'll take more questions later on. Negative delta G naught is saying equilibrium is tilting towards the product. Positive delta G naught is reaction going towards the reactant. We use the delta H naught, or the standard enthalpy of reaction, to describe whether the heat is being absorbed or released for a chemical reaction. Or if we have an exothermic reaction, that's effectively of saying we're forming the more stable product. If we have endothermic reaction, we're effectively saying we're forming less stable products. Right. And then we use this knowledge to come to the conclusion, in order to have an acid being able to dissociate more proton, or the Foley dissociation of proton. In this general reaction of HA dissociating into H plus and A minus, we're talking about the relative equilibrium of this dissociation reaction. Or the other way to put it, the more complete this dissociation is, the stronger acid we're talking about. For example, HCl will fully dissociate into H plus and A minus, and because HCl is a strong acid. Right? Alternatively, if we're looking at HF, which is a weak acid, it's only going to partially dissociate into H minus and fluorine minus. And what drives this equilibrium? Right, so H plus is the same for all cases. What drives the equilibrium is that if we have more stable conjugate base of the acid, we are more likely to drive this equilibrium towards the right-hand side, or the dissociation of the acid. So hence, we come to the one important conclusion when we're trying to predict acidity, that is, more stable conjugate base means stronger acid. All right, and this rule comes from the thermodynamic principle of a Bronsted acid-base reaction. And there are several rules we went over talking about acidity of a molecule. That is, without knowing the pKa of the molecule, how can we predict the relative acidity of organic molecules or acidic molecules based on their molecular structure? We went over 5 different rules. First one, electron negativity of the anionic atom. So that means if we're looking at, where's my periodic table? Okay, so that's on the other hand. So if we're looking at atoms of the same row, of the same period, so their size will be similar to each other. The electron negativity goes from fluorine being the most electron negative, oxygen next, nitrogen weaker, and carbon even weaker, right? So electron negativity decreases. And that means if we're looking at the same row, we have HF more acidic than water. more acidic than NH3, and then even more acidic than CH4. All right. On top of that, we discussed having electron negativity not only on the actual anion, but if my electron negative atom is neighboring to my anion, it also provides stability of that anion through inductive effect. So that's the trend when we're talking about, let's say, a bunch of fluorine substituted alcohol. So this one with 4 of them will be more acidic. The molecule with only 2 of them. And then the position of the fluorine also matters. And then the unsubstituted one. So in this case, 2 factors, right? 1 is the number of the electron negative atom. 2 is how far away are these electron negative atoms. Bottom line is more electron negative atom and closer electron negative atom will be able to stabilize the anionic charge and hence making stronger acid. We'll try not to ask you ambiguous questions, like we're not gonna ask you to compare this one with, let's say, I'm not gonna ask you to compare like this one with, like, for example, this one with only 1 fluorine. I don't ask you to do those kind of comparison. Right. I'll take questions at the end of each chapter. And next one, hybridization. So hybridization sort of works similarly to the electron negativity trend. But in this case, we're just gonna focusing on carbon. We're saying the acetylene, which means dissociation of the terminal hydrogen on the sp carbon, is more acidic than a alkene, a terminal alkene like an ethane, and even more acidic than your or sp3 carbon, ethane. So the reason behind this trend is that upon dissociation, this anionic charge on the sp carbon is closer to the nuclei, or the sp carbon is more electron negative than sp2 carbon than sp3 carbon. And then we have trend number 4, which is size of the atom. So this one is typically when we're going down the periodic table, especially in our last column for the halogens. So this could overrule our factor number 1, which is the trend of electron negativity. So in here, we're saying the H iodine is more acidic than HBr, then HCl, then HF. All right, so when using the electron negativity trend, typically we ask you a question within the same period. When using the size of the atom trend, we typically ask you the question of the same group. And at the end, we know that resonance or delocalization of the charges provides stability of the charged species. So likewise, resonance will be able to stabilize the anionic charge and hence stabilize the conjugate base and making stronger acid. So some of the example we did will be, let's say we have a phenol, and comparing that with, let's say, a linear alcohol. So this one, upon deprotonation, so we're losing a proton, we're forming a oxygen minus without any resonance, and deprotonation of phenol will end up with a negative charge on the oxygen that can be stabilized or delocalized throughout the ring. Let's see how to do it. So when doing this kind of arrow pushing, you want to make sure you're going like slowly, so you're not like missing the steps, like going over the ring. And for example, in this case, let me push this again, right? I want to push it to the neighboring group, and then now my carbon would have made 5 bonds if I push it there, so I have to push it the other way. And we can do that again. Okay, I'll take any questions on acid-base chapter 4. Yeah.
It's like 2 steps for the arrow, like the electrons first move once, then move again.
So when you do the arrow pushing, it happens at the same time. We're just using the arrow pushing to show the movement of the electrons. All right, so even if we're drawing 2 arrows, it doesn't mean this is a stepwise process. This is just showing how the electron is circulating around your molecule without any real changes. In reality, again, whenever we're drawing the resonance structures, all 4 of them coexist. It's not like we're actually doing reactions or something. These are the structure of a same molecule. All right? Yeah.
Just like that electron, like the double bond becomes the lone pair, not the lone pair stays a lone pair. That's a different pair of electrons.
The electrons doesn't know where they should be. Electrons are all the same. The electrons doesn't care if it's on a carbon, in a double bond, or a lone pair. Electrons don't care. All right, so the reality is like an overlay of all 4 structures all together. All right, any other questions on acid-base chapter 4? Yeah.
Do the 4 or 5 rules that we learned, do they only apply to Bronsted acid because we're concerned about deprotonation?
Right, so for these rules, we're specifically talking about Bronsted acid base. The concept of stable conjugate bases, well, for Lewis acid base reaction, you do not have a conjugate base. Right, so these are specific for Bronsted acid base reactions. Okay, then let's move on to chapter 5. Chapter 5 is a very short chapter, basically just talking about what is the overall structure, nomenclature, and physical property of alkene. So this chapter, we start by talking about degree of unsaturation. Like that's defined as degree of unsaturation is H reference. So H reference is a number of hydrogen in a molecule if everything is saturated. So that is 2n plus 2, where n is your number of carbon. And then minus H molecule. So this H molecule equals the number of your hydrogen plus the number of your halogen minus the number of your nitrogen. All right. So some of the question we could ask you for the degree of unsaturation is like this one. This one I took it from one of my previous 14C exam, which says the molecular weight of a mysterious molecule is 82 gram per mole. And we tell you this molecule only contains carbon and hydrogen atoms. Calculate the DOU of this molecule and then draw one possible molecular structure. So the way to approach it is like, okay, so the molecular weight is 82 gram per mole. Let's see what is the possible number of carbon we can have in this molecule. Let's say if we have like 7 carbon, so that would have like 84 gram per mole, at least 84 gram per mole, not considering any hydrogen, so this is definitely not true. What if we have 6 carbon? Well, so that's going to be 6 times 12. That gives you 72 gram per mole. And we know that this molecule only contains carbon and hydrogen atoms, so the molecule will be C6H10. All right. And as a sanity check, you can also see like, what if I only have 5 carbon and a lot of hydrogens? So 5 carbon would be 60. So that means we're expecting like 22 hydrogens, and that's not possible, right? So you don't have something like C10, H22. It just doesn't work. So from the C6H10 that we derived, well, first of all, write the degree of unsaturation. So my degree of unsaturation equals to 12 times 2 minus 10. Right, so 12 times 2 is the 6 times 2 plus 2 divided by 2, and we get the degree of unsaturation of 2. So that 2 can come from either a carbon-carbon double bond or a ring structure. Right, so a ring is 1 degree of unsaturation, a double bond is 1 degree of unsaturation. So there are multiple ways we can do it. It can be, well, 1, 2, 3, 4, 5, 6, can be 2 double bonds. It can be a single triple bond. But again, if you're drawing a triple bond, make sure it's linear. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 carbons. Or it can be 1 ring, 1 double bond, 6-member ring with a double bond. Or it can be 2 rings and no double bond at all. It's a weird structure, I know, but. And for this one, let's just check how many hydrogens do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. 1, 2, 3, 4. Oh, I only have 5 carbons here. This is why. All right, so for this kind of question, it's more like an open-ended question. So you can have like multiple answers that are all correct, but the bottom line is knowing how to apply the rules and draw appropriate molecules. And then nomenclature. So one thing that lots of people were asking is for these kind of alkenes, it looks like we have a very long name. How do we approach it? So the best way to look at these names is I'm thinking about how to read, like for example, write the chemical structure of this E26-dimethyl 2,6-octadiene. All right, so we read it, we'll be like, okay, so this one is a octadiene, and that means we have 2 double bonds. Octa is saying we have 8 carbon in my main chain. And then E here is saying my double bond is having the trans configuration of the higher priority groups. All right, so let's just write the 8 chain first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Right, 1, 2, 3, 4, 5, 6, 7, 8. So my double bond is in position 2 and 6. So that's here, 1, 2, 6. And then we add the methyl group there. So methyl group is in position 2 and position 6. And at the end, let me check if my stereochemistry is correct. Now looking at this one, the first one. This one doesn't have stereochemistry because both of these groups on my left carbon are methyl. So easy nomenclature doesn't apply to my position 2 double bond. It's not chiral. Or this is not a stereocenter, the best way to put it. Alternatively, this one is a stereocenter. So when we look at the EZ configuration, E means we have high priority group trans to each other. And the low priority group also trans to each other. So when we say high and low priority group, we're specifically looking at the carbon, the sp2 carbon. So in this case, we'll be focusing on my carbon 6 and carbon 7. Right, so among my carbon 6 and 7, this one will be my high priority group, so around carbon 6. The bottom one is high, and the top one is low. Right. What about carbon 7? If we're focusing on carbon 7, then we have a CH3 group and a hydrogen. Comparing your CH3 with a hydrogen, your CH3 is a high priority group, and your hydrogen is the low priority group. All right, so that's why this is a E configuration, high priority groups trans to each other. The most important thing here, if you're confused in how to assign it, is focusing on one sp2 carbon, arrange the priority, and look at which one is a high priority group. Yeah. What do you mean by? I don't think that doesn't happen. Like, you have plenty of examples you can practice on, but do not alternate the question and ask like what else would happen.
I think what you're saying is like if you're naming it and the two groups had different like stereochemistries, like one was E and one was Z.
Then we have to write both. So the way we're naming it is only one of them is a stereo center. The left one is not a stereo center, so we don't have to say it.
If it was, well, how would you write it?
Then you have to write it in front of each. All right, and physical properties are pretty straightforward. Terpenes and isoprenes, just focusing on the skeleton. And for the isoprene, they do have double bonds. I don't care about how you draw the terpene structure. And I don't care how you draw the isoprene structure, just find a breakpoint. And I want to spend a little bit more time on premier 1, which is the reaction mechanism profile. Now, I've shown you this diagram before, right? We were talking about the thermodynamics describes the relative stability of your A to B, and then kinetics describes the energy differences between your reactant to the transition state. So here, I want to link the potential energy surface here to something we discussed in class together. Like, I always get the question in like, oh, when we're drawing selectivity, like why this is not happening? So the reason when we say something is not happening, it's not because I say it or something, it's because of thermodynamics. So if we think about an elementary step of the alkene adding onto the proton, right? We do the arrow pushing like this. Now you can potentially form a secondary or a primary carbocation. So if we put this elementary step onto our potential energy surface, effectively we're having some kind of energy. Our start point is the same, alkene plus H plus. And we have some transition state I'm not going to discuss, but what we're forming is either a highly unstable primary carbocation or a relatively more stable secondary carbocation. So if we're looking at the thermodynamics here, we're talking about the energy difference here. The formation, the delta H formation of my secondary carbocation is going to be smaller than delta H formation of my primary carbocation. All right, so when we're saying whether or not this reaction is taking place or not, we're not forming the primary carbocation because this is like thermodynamics. So thermodynamics dictates like you're forming less of the primary carbocation. And if you think about our relationship between like Gibbs free energy and your equilibrium constant, we have delta G naught equals to negative RT log K. Right, so my K here states equilibrium constant, right? So the larger the differences, the less likely you're forming that product. All right, so it's not like I say it's not happening, or like it's just because the nature of the stability of the carbocation suggested it cannot take place. And what about an alternative way of thinking? Another example we have is, let's say we're looking at a carbocation rearrangement. So I'm just going to write my carbon-cation rearrangement. Let's say we start here. We have a secondary carbon-cation. And someone was asking me, now if these will have like hydrogen that can also potentially shift to form that primary carbon-cation. All right, and someone was asking, so is that never happening? Right, so if we think about the process of this rearrangement, what are we having? Again, we have a energy, that's my y-axis, and then in this case, my starting material is my secondary carbon-cation, and I can potentially form this unstable primary carbon-cation that is uphill. Or we can have a correct carbon-cation rearrangement. When we say correct, it's because we are forming the more stable tertiary carbon-cation. All right. So when the reaction is taking place, the nature of the reaction is it will find some pathway, so it's going lower in energy. Right? So in this case, it's much more likely to have the reaction taking this pathway as our correct pathway. And the other one is not taking place. Again, not because I said that, it's because thermodynamically, your molecule just doesn't want to go uphill if it has another choice. All right, so like when we're drawing the reaction mechanism, those minor pathways or the higher energy pathways will typically be like concealed from you, but it doesn't mean they still have a chance of happening. Like in this case, it's actually a competing process. It's like you're competing with a lower energy pathway, which is physically taking place. Okay, I'll take any questions if we have, because this might sound a little bit new to you. No? We're good. All right. And then from here, yes?
You had something right earlier that like the delta H of the primary would be greater than the delta H of the secondaries.
Yes.
Wouldn't that be the opposite of what you're saying? Because isn't delta H the change in energy?
Well, remember, when we're having the product being higher in energy than your reactant, we're saying your product is less stable than your reactant. It's endothermic. The transformation of a secondary carbon-cation to a primary carbon-cation takes energy. Alternatively, if it is exothermic, then we're saying my product is more stable than your reactant. Right? So this transformation releases energy. Yeah.
If we add nitrogen to the system, why would it want to go to a less stable version?
Well, again, thinking about it this way, even if you're adding energy to the system, you're adding energy to both pathways. All right, your starting material is making a choice between a lower energy pathway or a higher energy pathway. If you're adding enough energy to the pathway, then we're just eventually having this one being a reversible process, meaning after we form this one, it can go back to your starting material, oscillating between these two structures. The bottom line here is you have to think about your intermediates. Your molecule is making a choice. It always wants to go to the energetically most feasible pathway. Like if you think about like you start from some kind of energy, like that energy comes from our thermal energy or our room temperature, right? So you start somewhere and you always want to go downhill. If possible, you want to go downhill in that process. It's like if you go to a ski trip and you can choose to go downhill or like go uphill, the chances are you will go downhill. Yeah.
For terpenes and isoprenes, just because they weren't like in the worksheets, like where do you like where should we go to like study that?
Sorry, what's the question again?
For terpenes and isoprenes, just because we haven't really covered that a lot.
Yeah, it's just finding the breakpoint, that's all.
Okay. Would you say like textbook problem?
Yeah, textbook kind of problem. Yeah.
So for this upcoming exam, we should be bringing a calculator in case we need calculating.
yes, well, not only delta G, but also like pH or pKa. So if you have a calculator, do bring one. Yeah.
So when you want us to draw the favorable and unfavorable product, are you gonna point that out as a question, or should we always assume that we're drawing both pathways?
So if we are not specified, so for example, in this case, this is not going to be formed. It's not even like favorable or unfavorable. It's not like major or minor product. Even major or minor product, both of them are favored, right? So in this case, this is not, this is why I'm explaining you should not consider this pathway because it is not taking place. Now in the exam and also in our text, in our worksheet, we'll say like, okay, predict the major product of the reaction. Or if we give you major and minor and ask you to write reaction mechanism to show how they're being formed. All right. And let's keep going on this part. And then this part is all, and then the rest of the premier one is a quick overview of like how do we do error pushing. We did a series of elementary steps. So one thing to keep in mind is for error pushing, we use it to demonstrate electron movement in a single step. That is, if we're doing this kind of like, if we're doing this kind of 1-2 shift, then we're only using arrow pushing to show the 1-2 shift. You do not do it in separate, because after we form, for example in here, after we form it, we can have a nucleophile coming in and react with that carbocation. But we do not combine and do it this way. This is not correct. Like, don't add it. You have to do it in a stepwise fashion because we're forming this intermediate, right? And let's just quickly do the arrow pushing for all these structures. I'm just going to do it on my iPad while going through the name of these elementary steps. You should already know how to do it, like dissociation of the polar covalent bond. So the electron in the double bond go onto the more electron negative atom and then ends up forming a cation and an anion. Next one, homolytic cleavage, means the 2 electrons in your single bond, one go to the left, one go to the right. We end up forming 2 radical species. Secondly, the third reaction, formation of a covalent bond. Well, so we push it this way, and the result is we're forming a new bond between your atom A and B. Or if it is a radical reaction, we do single-sided arrow that meet in the middle. It's also forming a new bond between your X and Y. For substitution reaction, means we're simultaneously forming a XA bond while breaking the AB bond. So for this kind of reaction, it's still a single-step process, even if we're drawing it with 2 arrows. In the transition state, we're saying the bond between your X atom and A atom is partially formed, and the bond between your A atom and B atom is partially broke. And then we have addition. Now you can have the nucleophilic addition onto a polar covalent bond, like a carbonyl group. So that will go like this, right? So we're forming a new XA bond. We're breaking an AB bond. We can also have electrophilic addition, where your double bond is acting as a nucleophile. So that's going here. You're forming a new bond between your carbon and electrophile, and the radial selectivity depends on the stability of your carbocation. I didn't draw the things here, but all right. And then in this part, we have also discussed the relative stability of your reactive intermediate. So for carbocation and radical, the tertiary carbocation and radical are more stable. For carbanion, the tertiary is the least stable. All right. Okay, I only have 10 minutes left. And then we have 2 more chapters that should be more fresh for you. The alkyne is more fresh for you and synthesis. So let me spend some time to go over one example into how to write the mechanism of a reaction that you feel you've never seen, right? Don't be afraid of it, how to analyze the problem. So this one is pretty straightforward. You can do it yourself. And you can find the answer in our annotated note as well. The next reaction here is, let's say we have this interesting reaction. This is also in your textbook. And we want you to write out a mechanism of this reaction. How do we do it? All right. So for this problem, there are a few analyses we can do by simply observing what is going on. For example, in this one, we observe my starting material. I found two pieces of interesting information. First piece, this is a carboxylic acid, or we have a very acidic hydrogen, right? So that's a hydrogen attached electron negative oxygen, which is also delocalized over resonance. So the hydrogen I selected is very acidic. Or what does it mean? It means in my reaction condition, I have NaOH. So this is a hint of at least a Bronsted acid-base reaction is taking place. So we have HA reacting with OH minus to give you A minus plus H2O. Right? By simply observing the structure of my starting material, be like, okay, we have an acidic hydrogen that's going to react with the NaOH group in my reaction mixture. What else do we know? We have a double bond, and we have Br2 as our reagent. So you can go over your lecture note for alkene. You'll be like, okay, so in halogenation reaction, we have these kind of double bond adding onto the Br to form a bridged carbocation intermediate. All right. What else do we know? Well, we also have this one, or it's the stereochemistry of the two group that gets added onto the double bond. So we have a Br added onto the double bond, and somehow we have this oxygen that's coming from the same molecule add onto the double bond, and my Br and the oxygen is on opposite side with each other. Or this reaction is an anti-stereoselective. All right. So then the question becomes, what is going on? Let's do it step by step. First thing, as we were saying, you have an acidic hydrogen that will get deprotonated by the NABH. So let's just draw that first acid-base reaction. Right, so this is just the general acid-base reaction. And what are we going to form? We're going to form something like this. Everything else stays the same. And hydrogen and my oxygen gets deprotonated. Or if we're doing the arrow pushing, that's something we're doing. And we're forming H2O as my side product. And we already see like H2O is in my product. And so, well, my first step is probably just the acid-base reaction, right? So we're happy. What about the next? Now, this is a double bond. This is a nucleophile. So the nucleophile is not going to direct interact with my double bond. Next step must be a nucleophilic addition of, well, so it must be an addition to my double bond of my Br2. So let me use my Br2 here. And my double bond attacks the Br and breaks the Br-Br bond. All right, so my next step, my product becomes this one. And, well, for selectivity, I don't know, but in the product, my Br is added on the top carbon. So let me put my Br on the top carbon for now. It only asks me to predict the reaction mechanism. It doesn't ask us to explain everything, right? So you can get information from your product when you're questioning, like, oh, what's the selectivity of this step? And in this case, this is going to be something like this. And we have this carbocation. And we know that this is a bridged bromine. And I'll take questions after I finish. So you know that this is a bridged bromine. And we have carbon, oxygen, and the carbonyl on the negative sign on the oxygen. And the side product here is a Br minus. And I look at my product, I'll be like, okay, so Br minus is being generated as one of my side products, so I'm on the right track, right? So that's how we figure out the second step, and what's in the question is actually helping me in solving the problem, especially in the side product that's being generated. And what about the last step? The last bond we're trying to make here is the new carbon-oxygen bond. And what does that look like? Well, so that's my oxygen, and that's a carbocation. So the last step is this nucleophilic addition onto the carbocation from the opposite face of that bridged bromine, which is as we expected. And what's the product of this last step? Well, we're going to form something like this. Carbon, oxygen, oxygen here, and then hydrogen, Br, hydrogen. All right. And you look at our product, is that the same? Yes, so we're happy. Right, so that's how we work out the mechanism of this intramolecular addition reaction. You get information by reading what is my reactant, what is my reaction condition, and what are the side products, right? How do we work it through step by step? Okay, any questions? Yeah.
Does it matter which step goes first, making the oxygen?
It doesn't matter. And in fact, in this reaction mixture, this does not exist. So under basic condition, this acid-base equilibrium is constantly taking place. Depending on the pH of your solution, most of your starting material will be in its conjugate base form, right? So how we draw it, it doesn't matter. But I tend to draw the acid base first because this equilibrium is constantly taking place. Yes?
Do you want us to draw resonance in our mechanisms, like with a bridged bromine? Like, do we have to draw resonance structures, or can we just draw the major?
I would say you do not have to draw everything, but in the question, we might specify draw all resonance form that are relevant. But if we did not specify it, it's okay.
Do we need to show the breaking of the bond in sodium hydroxide?
Is sodium hydroxide have a real bond in aqueous solution? Right, so keep in mind, the strong base is going to fully dissociate in your aqueous solution nevertheless. So you don't have to draw a real covalent bond between your sodium and OH minus. All right, I'll take more questions outside, and I have two more practice examples. One is a synthesis example. One is, again, a reaction example. So you can check the annotated note for these examples. And good luck on Friday. Kara and Jeff will be with you on Friday. Your LA is hosting review sessions tomorrow, I believe. I posted the time on there.